This is the Naked Mole Rat podcast by Libo Studio. I'm Ilya Kolmanovsky. I'm initially trained as a zoologist, but I turned into a science journalist, and my job is to talk to the scientists from all over the world. We do this show every 2 weeks in Russian, but many interviews are conducted in English, so we decided to go ahead and put them online with only some minor edits done to them. Our guests are world-class experts, and they usually have a great way of telling stories of their discoveries. So we're asking you, make sure to hit all the subscribe and like buttons, and please spread the word so that your English or Russian-speaking friends discover the Naked Mole Rat podcast. This interview comes from an episode on machines learning from children and like children. Alan Turing has famously stated that if we want robots to learn to do things that are hard for them, like living in the material world, operating physical items, and interacting with real humans, if we want artificial intelligence to succeed at all that, we need to make sure that they are learning like babies, not like adults. But how do babies learn? There is no other expert on that subject better than philosopher, experimental psychologist, and writer Professor Alison Gopnik from University of California at Berkeley. Her group has performed endless experiments on untold number of babies to figure out just that, how babies conquer this world. Her most famous book on the subject is The Philosophical Baby. We spoke about children and artificial intelligence during spring via Zoom, and here's a full version of this conversation.
Yeah, my family is Russian, as you could probably tell from my embarrassing last name. And I've never been there, even though my grandfather emigrated from Zhytomyr, was where he actually grew up. So one of the things on my bucket list is getting to Russia, which in fact we were thinking about this year. But
do you speak any Russian?
I actually took Russian when I was in college, partly because of this sense of but I don't think I can remember, I might be able to get some of it back if I heard it again, but...
Would you be able to introduce yourself in Russian?
I don't think so. So I'm Alison Gopnik. I'm at the University of California at Berkeley. I'm in the Department of Psychology, also affiliate in philosophy, and also a member of the Berkeley AI Research Group.
Could you please explain to me how come you, as a psychologist and a philosopher, how come that you collaborate with AI people?
Yeah, so from a cognitive science perspective and from a philosophical perspective, I think the best idea we have about how the human mind works is that it's some kind of computational system. We don't know exactly what kind, but it's some kind of computational system. And so if you're trying to figure out how it works, a good way to do it is to try and say what kind of computations could lead to the same abilities that we see in, say, very young children, and vice versa. If you're trying to design a system that can learn in particular, then children are the best learners that we know of in the universe. So it makes sense to look to them to see what are some of the features of how they solve the problem of understanding about the world that a computational system could do as well. And from a philosophical perspective, the problem that I've always been the most interested in is how is it that we can learn as much as we do about the world, given how little information actually reaches us? So all we get are these photons hitting our retinas and disturbances of air at our ears, and yet every single one of us knows about other people, things, everyday objects, and eventually, we get to know about Einstein's theory and things that are very far away and very small. How's that possible? What are our brains doing or what could any system do that would enable it to solve that problem? So again, children's brains are a system that we know really does solve that problem. And that's one of the big problems that AI will have to solve.
What can AI learn from children? Is there already some understanding of that?
Well, it's interesting because in, the very first classic Alan Turing paper where he introduced the idea of the Turing test, that you might try and discover whether a computer was intelligent by comparing it to a person. And it's funny because in that paper, about halfway through, he says, maybe this is just not the right idea. Maybe if we really wanted to design an intelligent machine, we shouldn't try to make it be like an adult mind. We should try and make it be like a child's mind. Because after all, the children are the ones who are learning all the things that allow adults to be intelligent. And he has a very interesting discussion about what that would mean. And that half of his paper was just sort of, everyone ignored it for 40 years until this latest AI spring, where we've realized that the reason why we've had these great advances is because we're starting to design systems that learn rather than designing systems that have intelligence programmed into them in the first place. And when you start thinking about systems that learn, this analogy to children becomes even more important, because we know that children are the best learners we have. And if we look at the way that the new machine learning systems work, they're very different from the ways that children work. And they're different in ways that mean that they have some pretty serious limitations. So they need very, very, very large data sets. And we know that children can learn from just a few examples. They need supervision. So they need to have, say, someone is telling them, label this as a cat or label this as a dog for something like ImageNet, or in things like reinforcement learning, someone is saying, okay, your score is getting better, you're getting more reward, you're doing better in this game of Go. And children get very little of that. So they get very little supervision, very little reinforcement. Occasionally someone says, oh, good job, but that's about it. And nevertheless, they're able to learn as much as they can. And the AI systems that we typically have are not very good at generalizing. So they might be able to say, identify this one's a dog and this one's a cat, but then you can show them an adversarial example, something that isn't actually like a cat at all, but has some of the same texture properties as a cat, and they'll identify it as a cat. Whereas kids are incredibly good at generalizing. So again, not just from a few examples, they can with just a few examples, they can have new hypotheses about what's going on in the world that are sort of wonderfully strange and also make sense. An example that I heard recently, actually from one of our AI students, was her 4-year-old she'd taken to the campus at Berkeley. And Berkeley has a famous campanile. It has this famous bell tower in the middle of the campus that has a clock at the top. And the little boy looked at this tower with a clock at the top and said, there's a clock way up there. And then he said, why is there a clock way up there? Of course, if you think about it, right, it's weird to have a clock up in the sky. And he said, maybe it's so the children and the students won't break the clock. So they put it high up so that the children and the students wouldn't be able to break it. Now, that's not a hypothesis that any grown-up would have about why the clock is up at the top of the bell tower. But it's actually a pretty good hypothesis. It makes sense, especially if you're a 4-year-old and you know that mom tends to put things up high so you can't get to them. And there's a zillion examples of kids being able to make those kinds of generalizations, not something that any of the AI systems that we currently have could do. By the way, I often use as examples, there's a marvelous book by Kolmanovsky, actually, a Russian, wonderful Russian writer and developmental psychologist. And he has a book that's just examples of all these strange, interesting generalizations and things.
2 до 5.
Yeah.
From 2 to 5.
Exactly. From 3 to 5. That's it. One of my favorite developmental psychology books. And it's just full of these marvelous examples of things that our current AI just wouldn't be able to do. So if you want, what you see with current AIs is with lots of data and lots of supervision, they can make pretty narrow generalizations, whereas with kids, with rather little data and not much supervision, they can make really striking and appropriate generalizations. So what are they doing that we could import into AI? So our project, the project that I'm working on with people in Berkeley, one thing that I discovered is that in computer science, everyone loves acronyms. It's very important to get the right abbreviation. So our project is called MESS, which is appropriate for children and stands for Model Building Exploratory Social Learning Systems. So those are the 3 things that we think that the kids are doing that current AIs, at least, the most established ones, aren't yet doing. So one thing that the kids are doing is, rather than just sort of doing statistical generalizations from the data, they're actually building models. And in the work that I've been doing for the last 20 years, we've shown that they're building causal models, something that looks like the work that Judea Pearl, who got the Turing Award, has designed these causal graphical models or causal Bayes nets. And we've shown now for 20 years that children are doing things that look a lot like causal graphical model or causal Bayes net inference.
What is this?
So the way that these things work is really very much like the way that science works. So my first book was called The Scientist in the Crib, and I've argued for a long time that children are making up intuitive theories like scientific theories. Now, what do scientists do when they make up a theory? They take a bunch of statistics, they take a bunch of outcomes of experiments, and they use it to build a causal picture of the world. Here's the things in the world. This makes this thing happen. This makes this thing happen via another thing. This is a common cause for two other outcomes. And it turns out that you can do really beautiful computational work showing how you could go from a bunch of statistics to this kind of abstract causal structure. And if you do that, this causal model gives you a much more powerful representation of the world than just the statistics, just the data would be. So it's like the difference between, Tycho Brahe, the astronomer who kept tables of what all the patterns of all the planets, and then Kepler or Galileo, who actually can say, oh yeah, here's a model of how those planets are working, and it explains all the data. Mm-hmm. And children, from the time they're 2 years old, seem to be taking data and then abstracting these causal models. The poor AIs are actually sort of stuck inside of their computers. And one of the things that we know that children are doing is actually going out and doing experiments on the world. Again, analogous to scientists. Now, when the children do it, we call it getting into everything, but we know that that's one of the things that even small babies are spending a lot of their time doing. And a lot of work that we've done recently has shown that it's not just that they're randomly getting into everything, they're doing things that are designed to give them the maximum information to solve the problems that they're trying to solve. So we've been building and using curiosity-based AIs, for instance. There's a lot of interest in this, where instead of having a reward about did you reach your goal, the reward is did you find out something new? And we can use those as models for an AI rather than the typical sort of did your score go up? And we can use children's exploration as a model for those kinds of AIs. And then the third piece is the S in MESS is social learning. So one of the things that we know that children do is, rather than just learning by themselves, or rather than learning with a tutor who's telling them this is right and this is wrong, they're very good, amazingly good in very subtle ways at, say, seeing what someone does and imitating it and picking out the right pieces to imitate. So in robotics, for example, a standard method for trying to train robots now is to give them a human demonstration and then get them to use that information to design their own action. So, you get a video of a person reaching for an object on a desk and then see if the robot will do it. But again, there's this generalization problem, which is that the robots can imitate exactly what you do, but now you just change the problem a little bit. You just put the object, a few centimeters to one side, and now the robot falls apart. And one of the things that we know from children is, again, from the time they're babies, from the time they're infants, they're imitating what people do, but they're imitating in this very intelligent way where they can figure out this is what the person was trying to do. So I should do something that's trying to accomplish the same goal. Or even this person was trying to teach me, so that means that I should pay attention to all the fine details of what they do, versus this person just did this by accident, so the fine details don't matter. So we're trying to design AI systems that can learn from imitation in this smarter way rather than just imitating every detail.
I think there is a couple of things that came up in my interview with Alexei Efros, which really struck me.
We're mentioning here Professor Alexei Efros. He is a computer scientist. I came across his work, which he did in collaboration with Alison Gopnik. He's breeding neural networks, which are having a semblance of a childhood. They learn to get bored, to explore, and to see the exploration as a sole reward for their actions.
One thing is, he said, so we got that curiosity-driven neural network, but here's a problem. We can give it a coin, and if it starts flipping a coin, it will probably do that forever, trying to find a pattern. Its curiosity is unabridged, and it would find patterns everywhere. Just like those stupid people in Las Vegas who think that they are onto something and that they are finding a pattern. And I said, okay, so children are better than people, are they? Are children better than people?
Well, one of the things that we've been doing in my lab for a while, and one of the things I've argued, is that a really deep, basic problem in computer science is what's called the explore-exploit trade-off. So the problem is, how do you get a system that can explore, consider different options in an intelligent way, and also can exploit, can use the information they find to actually do something efficiently and effectively? And dating all the way back to the beginnings of computer science, it turns out to be essentially impossible to get a system that will maximize both of those things. And one of the things that I've argued is if you look at children are sort of the explore part of that trade-off. So you could think about childhood as being evolution's way of solving the explore-exploit trade-off. Because what happens is you get this early period where you just explore and you don't actually have to act very effectively because you have parents and others who take care of you. And then you take the things that you explored when you were young, you put them to use later on to actually exploit. So if you think about that picture, and this is relevant to Alyosha's point, noisiness, for example, variability, stochasticity, liking things that are sort of random is a good strategy if you're an explorer. It's not a good strategy if you're an exploiter. So if you want to just do things effectively, it's not a good idea to do them in a way that's variable and random and noisy. But if you want to explore, it is good to be variable and noisy. But the problem, the place where I think the great interesting challenge is that, as that example, those Tchaikovsky examples show, the children are really interesting because there's definitely more random than the adults. And what we've shown in my lab is that randomness makes them better at solving certain kinds of problems. So it actually makes them better at learning things that are unexpected or unusual. You could sort of see why, if you're willing to have more different alternatives bounce around among different hypotheses or different solutions, you're going to get to things that are more unlikely. And in fact, we've shown that that's exactly what happens with children. Children do much better than grown-ups on a task that involves finding out an unlikely outcome or coming to an unlikely hypothesis. We did a bunch of experiments most recently where let me see if I can quickly describe this. So you have a machine this is the famous Blicket detector. So this is a machine that lights up when you put some things on it, not others. And there's a rule about how the machine works. And sometimes the rule is an obvious one, like, white things don't make it go and black things do make it go. But sometimes it's more subtle, like white and striped things will make it go, but nothing else will make it go, right? And so you could have these simple one-dimensional rules like the white versus black, or you could have these more subtle, unusual rules like it has to be both.
The Blicket detector is a machine which is programmed to play music in case the right Blicket is put on top of it. Blicket is not a real word. The experiment subject needs to figure out what a Blicket is if, for example, one black round item combined with a white item of any shape is a Blicket. Is a Blicket enough to make a machine play? Blicket detector has been used in many experiments to investigate the ways children and adults come to conclusions.
And it turns out that if you give data about that kind of rule to adults and children, the adults very quickly go with the simpler rule, the one-dimensional rule, and they won't even try to find data that goes against that hypothesis. Whereas the children, because they're impulsive, because they keep putting things on the machine, they keep wanting more and more data, end up being able to figure out this more unlikely rule where you actually have to take two dimensions into account at once. And another interesting piece about this study is that you can set it up so that if you get it wrong, you actually have a loss. kind of classic thing that you would have with something like reinforcement learning. So if you get it wrong, you lose stickers or you lose points. And for adults, that makes them very conservative. So they don't want to try something if they'll lose. They don't want to try to get more information if they'll lose points. But for the children, especially the preschoolers, even though they're a bit disappointed that they're losing the stickers, it's so much fun to find out what's going to happen if you put the block on that they keep trying and they keep experimenting, even if it looks like there's a risk. And what that means is that's part of the reason why the children are learning better than the adults, because they're more willing to take a risk to get more information.
One last thing that came up in Alyosha's interview was this. If you buy a toy, it will fit a child of a certain age, but not younger and not older. Somehow children range their priorities and also in a sort of time sequence. How does it work in children? He said, I need to ask you.
Yeah, so that's a really good point. To get back to your point about, the random flipping and the curiosity agents, where I think the really interesting question is, how is it that children have enough noise and variability to try out new ideas, but not so much that they're just doing something that's completely random? And again, if you think about those Tchaikovsky examples, what makes them so fun and so interesting is that the children are clearly thinking more out of the box, more wildly, more imaginatively than the grown-ups. But it's not like they're just producing a random string of words, right? They're doing something that makes sense. And of course, that's what we need to do to make progress in science or in art or technology, is hit that sweet spot of things that are new and creative, but also aren't just random and crazy. And we can show, there's some really nice experiments that show, even with babies, for instance, what you can do is show babies different events that have different amounts of novelty or different amounts of new information. And you can quantify how much new information there is in each one of these events from an information theoretic perspective. And then you just see how long do these babies, these 9-month-olds, look at those events. So they get an event on the screen. How long do they look at it? And what my colleague Celeste Kidd, who's also collaborating in this project, has shown is that there's this kind of sweet spot where if the thing's totally random, there's lots of new information, but it's just because there's more randomness, the babies don't look at it. And if it's totally predictable, the babies don't look at it. But there's this point in the middle where there's enough new information to actually be able to make sense out of it, but not so much that it just seems random. And that's the sweet spot. That's where the babies are most likely, even the 9-month-olds are most likely to look at things that have enough variability so they're new, but not so much that they're actually just random. And there's a beautiful experiment, one of my favorite experiments by Amy Stahl and Lisa Feigenson at Johns Hopkins. And what they did was they showed babies, again, 15-month-old babies, different unusual, surprising events. So the babies would see a little toy car and it looked as if it came down a ramp and then it just stayed hovering in midair. Or they would see a little toy car and it looked as if it just went through a wall without the wall stopping it. And one thing they discovered was that the babies, then they would give the babies the toy car. And one thing they discovered was the babies would play much more with something that had done something unusual or surprising than something that had just done what they expected. So they were thinking about it in terms of what their hypothesis was and whether that hypothesis was violated. But interestingly, when they had the toy that looked as if it violated the rules of gravity, what they would do was try and drop it on the floor. Whereas when they got the one that looked as if it went through solid walls, they would bang it against the table. So their decision about what to play with depended on what their hypothesis was that was being violated. So in some ways, they're doing this novel action that they wouldn't normally do, but it depends on what their hypotheses about the world are and what they think is predictable and what's surprising. And what we'd need to have a curiosity-driven AI that was as good as the babies would be not just, I'd rather have things that are noisier or more random or have more information, but I'd rather have things that have more information with respect to the hypothesis that I'm entertaining now about the world.
Do you think that might be possible?
Well, we're giving it our best. We're giving it our best shot. The idea would be that if you put together the model building part, the idea that you have a system that's taking data and trying to build a model, and then the exploration part. So you have a system that is building the model, but also trying to, in a way, trying to show that the model is wrong a lot of the time. It is very interested in cases where the model is wrong. Put those two things together, and maybe that would be the formula that you would have. And I think, a lot of the approaches to AI have been very much like the classic philosophical approaches to solving this problem of how we know about the world. So one idea is, well, you could just build everything in, right? And that was kind of the old-fashioned AI idea, right? How do you solve the problem? Well, you just build everything in. And then the other idea is, well, if you just get enough data, you don't have to worry about it. You'll solve the problem. And that's kind of the more recent approach. And when we actually look at children, what we see is that neither of those things is really the right description. Somehow the children are taking data, they're constructing theories, then they're changing their theories based on the data. They're very interested in something that violates the theory. Then they alter the theory. Again, a lot like scientists. And it's that kind of back and forth between the theory and the data that actually lets them learn as much as they do. And the question is, could we design an AI that would do the same thing?
Garry Kasparov, he deals with children who learn to play chess. He's been doing it in the 80s. And back then he had wonderful students who knew the theory really well. Who could give all the reasoning behind any move they choose, compare it with the history of chess, compare it with the known moves, historically known moves. But he says that right now, children he teaches are trained by AI, are trained by computers, and here's the outcome: they play better. They are stronger players, but they're losing more and more an ability to explain any rationale behind the move they choose. They just know that this is the best move. What do you think about it? What's your take?
Yeah, that's a really interesting observation. And one of the questions that comes up again and again is what's the relationship between being able to have this explicit explanation for something versus just being able to do it implicitly or unconsciously. And one of the things that we see with children, for instance, doing these causal tasks that I mentioned, they obviously are doing really smart things about, say, taking all the statistics and making sense out of them, but they don't have very much access to that. So if you ask them, you could show them this very complicated pattern of blocks, and then you say, and they figure out which ones make it go, and then you say, how do you know that? And they'll say, well, okay, you put the blue one on and it made it go, and you put the red one on and it didn't, even though that never happened, right? They're just kind of confabulating that happened. They don't really track the statistics of probability, even though they use them. And I think a very interesting question for AI comes up with explainable AI kinds of questions is, when do we want our AIs just to do the right thing? And when and how do we want them to be able to explain it? And what advantages do we get from actually being able to explain it? I think that's a really interesting question that's up for grabs. And again, children can tell us a lot about this.
Or disadvantages sometimes, you can ruin a very beautifully performing algorithm,
right,
when you demand explanations. Sometimes it can do much better without explaining things at sort of a low level. It's interesting that the human brain is kind of able to go down to that level of functioning where there is not much reasoning, but very complex calculations and very complex, not just calculations, estimation. And what do you think about it?
Well, I think children are a wonderful sort of test bed for trying to figure out which pieces of our calculations are explicit, are things that we can articulate, and which ones aren't, and how do those two things relate to one another. So it isn't as simple as just saying, well, everything in children is unconscious, the way your visual system, for instance, to use the examples, is just unconscious. You don't know how it works. It's a little more complicated than that, but I think there can be some really interesting clues, because sometimes the children will be very articulate about saying, oh, okay, I know how this works. This one makes it go. This one doesn't. They'll even say things like, and if you hadn't put this one on and you had put the other one on, here's what would have happened. But other times, like if you say to them, how do you know that? They don't have any access to that at all. And I think that could be very important for giving us clues about when does having access help? What kinds of things does it help with? But when does, as you say, when is it that actually hurts what you're doing and you're doing something that's more complicated, too complicated to be able to actually articulate in words and language? I'm about in September, I'm going to go and spend time at Yoshua Bengio's lab in Montreal. And he's made these very interesting arguments about that you really need these kind of two systems. You need one system that is just pulling out the statistics without trying to have anything that's explainable. And then sort of on top of that, you have this attention-based conscious system that's trying to make, it's kind of like trying to make sense out of the brain, trying to make sense out of itself. And that gives you some of the advantages of explainability. And I think that's a very interesting approach that could give us a lot of progress as we go forward.
Can you say just in one phrase, what's your dream? What's your, pursuing that path?
For me, the dream would be understand what's going on in the mind of a 3-year-old. You know, what I would really like is if I could just sort of be teleported into the mind of a 3-year-old just for 10 minutes and see what does the world actually look like? What does thinking actually look like when you're 3? If you have 6 children, you will have had that thought where you look at them and you say, what is going on inside of that mind, right? Something really different from anything that I know about. So I would really like to personally to have a sense of that, but also I would like to have a scientific account of what is it that's going on? What is it that those brains are doing that makes them as powerful as they are? And how, not just for human brains, not just for child brains, but for any brain, for a Martian brain or a computer brain, what are the features it would need to have to be able to learn as much as we know that we can learn about the world?
Would you say goodbye in Russian?
I will try to remember my college Russian. До свидания.
After talking to Alison Gopnik, for me as a parent, the experience of watching my children will never be the same. It is not just cute when they fool around, play clumsily with items and words. It is actually their job, which shapes their super competent neural networks. We're observing a very important phase when they explore, while we are taking care of the exploit part. And this was the Naked Mole Rat podcast by Liba Liba Studio. I'm Ilya Kolmanovsky. Goodbye.